Hello and welcome back to Calculus 1. This is our first lecture of chapter 2, Intro to Limits. What is a limit? Well, I said that last time. It's a fancy way to compute the y value of the function. It's a really fancy way. We'll see why and how. So what we know from before is that if you have function, say y equals x squared minus 1, let's use f of x. If you have function f of x equals x squared minus 1, you can compute f of 3 as 3 squared minus 1, which is 8. So we replaced x with 3. That means we are replacing x with 3. And we have calculation 9 minus 1 is 8. This is your pre-calculus. Pre-calculus computes the value and walks away. That's it. Limit will compute the same value 8 in a completely different way, in a much more powerful way, and leave us opportunities to calculate certain cases where pre-calculus cannot compute. So let's talk about the idea of the limit computing x squared minus 1 as x goes to 3. This is our goal, to understand how to compute the value of x squared minus 1 as x is not just 3, but it goes to 3. Now, hopefully you understand the concept of going somewhere and being somewhere, right? Once you get to your destination, you are there. Going somewhere is the journey, it's the process. And that's where that change, remember how I said the calculus measures change? So limit fits in that sense in calculus because you have this arrow, the motion. X goes to 3. It's not at 3, it's going there. There is the process of getting places. So if I am to graph the pre-calculus problem at, let's say 3 over here, I would just put a point. That point would be at 8. So this point is 3, 8, and that's the end of the story. Single point shoots up, intersects the graph, bounces off into a y, and that's the answer, that's the value. So that's your pre-calc. What is calculus doing? The limit. I have to draw this one bigger. So let's say this is the graph, and your x equals 3 is, let's say, here. I can draw the pre-calculus situation. It was line going up, bouncing here, and giving us 8. Now that was pre-calculus. What calculus is doing is calculus is going to 3. X is going to 3. How do you achieve that motion on the line? Well, look, I'm going to approach 3 from the left. Literally walking on the line. So now, as I approach 3 from the left, I am actually translating that to walking up the line on a graph, which is translating into walking up the y-axis to 8. Do we all see that motion? It happens at the same time. pick a point here, it goes like that. Pick a point here, it goes like that. You see that as I'm getting closer to 3, you see how the other side is getting closer to y? So what I need you to picture in your mind is this green point moving towards 3, which gets you this point moving towards the corner, which gets this point moving towards 8. Can we see that motion developing? So as you are approaching 3 on the x-axis, as a consequence of what the function looks like, the other two are moving together with it in a swipe. Now I'm going to go from the other side and approach 3, which will send me down this line, which will send me down the y-axis. Do you see that as the red and blue collide at 3, the red and blue collide at 8? Do we see that motion happening? Great. That's limit, that's chapter 2. Let's go chapter 3. Yeah, that's it. X goes to 3. I need to see that motion on x-axis, and it will just transfer through as motion going around. Going around the function, and then eventually transfers to y-axis, which gives you the answer. The answer of the limit is the y value answer, and in many cases it matches your pre-calculus. So, fancy way to compute y value. One crucial thing to understand with limits, and I'm going to write that in blood over here. Limits compute at infinitely many points around the value, never at the value. So, limits compute at infinitely many values around x value and never at the value. So pre-calculus computes at 3. Pre-calculus computes at 3. Calculus computes everywhere else except at the 3. Calculus says, let's compute all of these values and then infer what the answer is. In that sense, as I am looking at limit x goes to 3 of x squared minus 1, I'm looking at the chart of values where I'm going to have 3 values on the left and 3 values from the right going towards 3. So what are my values on the left side? Well, I need to approach to 3, right, the red side. Oh, by the way, I call this Romeo and Juliet approach. It's a red and blue, right, for boys and girls. So now we have a Juliet approach. It's red. So what do we have? 2.9. 2.99 is closer to 3. And then 2.999 is even closer. So if you think of 3 as $3, you have $2.90, $2.99, and then you have $2.99 and 9/10 of a cent when you go to the gas station. Do you know that on gas station they actually charge that 9/10 of a cent? You never seen that fraction? When they display a price of $2.99 and then they have 9/10? Oh, you've seen that, right? That's 9 tenths. Please ask for change. Yeah. Why would they have that? Just, anyway. So, I have $2.90. $2.99 is closer to $3. And then, at the gas station, $2.99 and 9/10 of a cent closer to the $3. So, the limit wants to have answers to all of those. And all of the in-between ones, and the closer ones, and the further away ones. That's, yeah. So now, I'm going to go in my calculator here and calculate all of these values. Then, we are going to have the blue ones approach from the other side. $3.10 is far away. $3.01 is closer. And $3.01 of a cent is closer. So technically, instead of drawing these arrows on the graph, I am picking values that are getting closer to number 3 from both sides. And now I'm just going to use basic calculator to compute each one of these red and blue numbers in the function, provide their answers, and you will see that answers from the red are screaming 8, and the answers from the blue are screaming 8. And then we say, if it walks like a duck and quacks like a duck, it's 8, of course. Good. So let's go. Compute all of these on your own. You have your phones, right, with calculators. We need decimals. We need the precision there. Go on. Okay? Do we all see an 8? So you have graphic approach and you have calculations. Now, you would say, wait, hold on, this is way too easy. Well, yeah, that's exactly what this is. You are calculating values using the middle school method of picking x's and computing y's. The calculus upgrade is that you have to look at the trend of what those numbers tell you and infer the answer. So this is actually your exam question, because your first exam contains limit questions, and these are the first two methods of finding limits. We are going to have also a way to compute, do algebra and all of that. That's coming up in next lecture. But your first lecture on limits is not just understanding that limits compute a y value. That's it. It's also the ways. So way number one to find the limit of a function is to look at the graph. And you will be using that way a lot, especially when we start dealing with infinities and zeros. You will look at the graph and decide whether the limit is positive, negative, infinity, or zero, like this. That is your very first way to calculate limit of a function. Look at the graph and say the answer. Your second way to compute the limit of a function is to do the chart of values. This is very useful when you run into a very nasty limit to calculate. In terms of the algebra, too complicated or it didn't work the way you wanted it to do. So this is like a go-to method to solve every limit without learning anything else in the entire chapter, okay? Because you can always pick x values, because your problem will always include that x goes to some number. Goes to 3, goes to 5, goes to infinity, goes to 0, right? X always goes somewhere. As soon as you know where the x goes, you are able to pick the values and do this. So we already covered, just by learning what the basic limit is and seeing it in action, we already learned the first two methods to find the limit. On this, we're only going to add another 3 things, and we call it a chapter. All right, that's it. So it's very simple. Now, observe that the limit has what I call Romeo and Juliet, right? It has the red side and it has the blue side. Those sides have the name. The left side is approach from the left. That's the Juliet, red, right? And the blue side is approach from the right, the Romeo side. And then they either meet, and in this case they will meet at 8, or they don't. We all know how that ended. We don't? You do? I'm gonna spoil it if I say, yeah, they had a relationship and then they died because of it. There you go. I said it. Anyway, so what do we do? What do we do now? Now I'm going to take the red side and I'm going to say that this is limit x approaches 3 minus of x squared minus. So I put this minus in the exponent of 3. This is approach from the left. And then the Romeo side, blue, is going to be limit x squared minus 1 as x approaches 3 plus. That means approach from the right. So we have approach from the left, we have approach from the right, and those two together are called one-sided limits. We just gave them names. We didn't learn anything other than the notation and few new names. So every limit you take will have one-sided limits as a part of it. You have the limit from the left, which is the red stuff. You are literally approaching from the left. All of these numbers are to the left of 3 because they're smaller. All the blue numbers are larger than 3. They're to the right. They're larger than 3. You have to remember the notation 3 minus 3 plus. So minus will always mean left approach. So numbers will be smaller than the number you're observing. And then plus means to the right. We just need to make sure that they are approaching. Do y values have to line up and give us the same answer? The answer is no. And this is now where the first most important theorem of chapter 2 kicks in, and that is the theorem that says if these guys match, you have the limit, and it's whatever those numbers are. If they don't match, the limit does not exist. So this theorem is called 2.2 theorem, 2.2, but we're just going to say it's existence of limit theorem. So this is the major theorem for chapter 2. It says if limit of f of x as x approaches a minus is the same as limit of f of x as x approaches a plus. You know what? I'm gonna draw this blue. Limit of f of x approaches a plus. There we go. Is equal to L. Then the limit x approaches a of f of x, observe no plus and minus, exists, and it is equal to L. Otherwise, limit does not exist. This is the theorem which covers all of the limits for the entire education forever. Limits are going to show up in all of the chapters, Calc 1, a lot of Calc 2, second half, and then Calc 3 obviously, but they're in high-end computer science. They're there. They're there for electrical engineering a lot, so you'll see these limits a lot. Now, what does this theorem say? This is your red approach, left side minus. This is your right approach, plus. Remember how we got 8 for this one? Because the numbers were creeping up to 8, right? The blue numbers were creeping down towards 8. So we got 8 for this one in the prediction. We got 8 for this one in the prediction. So 8 equals 8, 8. And because they were equal, 8 and 8, the overall limit is 8. So since both were 8, we say the limit exists and it's 8. If one side goes to 8 and the other side goes to 9, well, limit doesn't exist, right? And that's exactly what killed Romeo and Juliet. Because they didn't show up at the same time, right? Read it, you'll see it. So bad things happen, right? One was there at 8, the other one was at 9, and they say, suicide is the way to go. Put themselves off, right? Easy. So answer to everything, right? So what do we have? We have left approach, right approach, and if they meet, that's the over limit. If they don't meet, limit doesn't exist. Now let's take a look at limit doesn't exist case. Cool examples are those piecewise functions. Let's say you have f of x, say x, when x is smaller than 0, and you have x squared plus 1, where x is bigger and equal than 0. We can solve this graphically and calculation. Let's do graphic approach and then calculation. So graph, we have x, open circle, and 45-degree line. So that's our piece before 0. After 0, we have to go at 1 and draw parabola. Okay, Juliet. The question is, what is the limit of f of x as x goes to 0, right? That's the question. So, Juliet, she's up first. As she approaches 0 from the left, right, red, that means you're going up the line and you are approaching 0. So it appears that Juliet, which is the limit x approaches 0 minus, is approaching 0 in a y value. So these are your answers are always y values, right? So as she's walking on x, let's say her shadow is walking on the line, which gives you where the y is gonna end up. So everything ends up at 0. Now Romeo, on the other side, goes down this line and he ends up at 1. So Romeo is the limit x approaches 0 plus, and he ends up at 1. Do they meet? No. See, at the same time, you can think of x-axis as time. At the same time, time 0, there are two different locations. Y-axis could be a location, separation in space, 1 mile apart, whatever. So Juliet is at 0, Romeo is at 1, and by our theorem, because they don't match, we conclude that the limit of f of x does not exist, D and E, as x goes to 0. Note the notation. This is not for decoration, the plus minus. And the red one has a minus, the blue one has a plus, and the black one over here has nothing. When there is nothing there, it's both of them at the same time approach, right? So they're both walking at the same time, and they end up in different locations. They don't meet. Limit doesn't exist. Cool? Of course, it's cool. It's math, right? Now, we can do the same thing now with a chart we did before. We say, okay, we are interested at this 0. Let's have 3 numbers for Romeo, 3 numbers for Juliet. Juliet is going to be 10 cents away, 1 cent away. These are all negatives. And then 1 cent away, 10 cents away, 1 cent away, and wait, it's supposed to be blue. From scratch, there we go. Now you have to be careful. The red ones, you have to compute in the upper function. And this is the skill that you are supposed to practice in pre-calc, but it's not really emphasized, so then you get slain when it comes to calculus. It's a piecewise function. The x works for red because those are the values smaller than 0. You set the values smaller than 0, you plug them in x. The blue values go here because the blue values are the values that are bigger than 0. So they go in this part of the function. Each piece of the function operates on a different part of the number line. This is your number line and this is where 0 is. Positive infinity that way, negative infinity this way. This is just a number line. And now I have to use my x function for red and x squared plus 1 function for blues. Okay, so x function is easy because it's just the same. So for Juliet, we get to copy these values as is. And clearly, Juliet is going towards 0. Now we have to compute Romeo. You get to square the value, add 1. So square value, so this is going to be 0.01. Square the value, add 1, 0 point, and you have 3 zeros and then 1. And then 1.5 zeros and then 1. And we see that Romeo is approaching value of 1 because the number of zeros is decreasing as you are going this way. So 1, 0, and then 3, and then 5. So this number is much closer to 1 than that one. When it goes to 1, it doesn't go to 0 because this one has 1, and this one has 1, and this one has 1, right? So now, that's not the same. And by the theorem I wrote earlier, if the numbers are not the same, the overall limit does not exist. Cool? Let's take a look at... Now, I never do the book examples because the book already worked out all of those examples. If you're interested, you will read them. I generally go in the homework and do some of those. But here's an example of what the book has. Example, find the limit for square root of x minus 1. These functions are tougher, right, than what I had. Do you care? No, because what are you doing? You're picking values and you're just plugging them in here. Sure, it's more annoying, but that's much different concept than harder, right? Two completely different concepts. Hard or annoying? It's annoying, it's not hard. You have to plug into this function and you plug in, look, 0, 9, 9, 9, 9, 9, 9, 9, 9, 9. They do 4 values each side. So we see that, see how this goes to 0.5? So it seems that Juliet goes to a half. Now you go to the other side, where you plug these values, and they are creeping up towards 0.5. This side 0.5, this side 0.5, so the limit for the entire problem is 1/2. So everything that I did with cheaper functions, you have a little bit more complicated functions, and then they go and talk about one-sided limits. So one-sided limit is just when you consider one side of the calculation. So left approach with a minus and the right approach with a plus, and those are called one-sided limits. So you see the notation, there's a little plus there and a little minus there. Graphs explaining everything I did before. So they draw the graph of the function and then they show as you are approaching from the bottom, as you are approaching from the top, right? So that's the left and right approaches, and they collide, in this case at 3. So 3 is the answer to the question. So that's that part. Then you run into some stuff that says no limit. See, as you start computing this, oscillations become too frequent. And if you try to compute this, you start getting infinities, right? Or you keep getting answers that you can't get a positive, a negative, a positive, a negative, a positive, a negative. Well, you can't have that, right? So in that case, any of those cases, limit does not exist. And we finally get to the homework. Homework exercises are there for you to practice. Now, as I said before, if you immediately go to homework exercises, you will probably start flipping the notebook looking for similar exercises done in class. That's a wrong way to learn calculus. You need to learn the concept of a limit. You understand, okay, I'm calculating y values, I can do that. There will be a value that is important, x approaches that value. Then there is a left and a right side, and then the theorem. You memorize that theorem, you're good to go for the entire chapter. Because that theorem says if the left approach and the right approach are the same, the limit is that number. Now, without giving you this particular example before, we are going to cover it after we're done with this, but before telling you how to do this problem, I have a question. What is the limit at 2 of a function? So what you have over there is open circle, and there is a dot right there. This dot is at 2, this is at 4. My question is, what is the limit of this function as x goes to 2? You said there's no limit? What do you say? 4? I'll keep my poker face no matter what you say, so neither of you gave the answer, gave the reason. You think?
So the notch in the circle doesn't include that number, right? So it just has a 2 value?
Yeah, the value is not there. Value is displaced, so value is at 2. So your answer is now 2,
Yeah.
and his value is,
Yeah,
what, you're going to take it outside,
yeah.
work it out, come back in, or I don't know. Let's see what the girls do. We'll go now to this side. What was Juliet's side? We got the room. What do you do? It's so funny when you start 5 girls. Like at least one. Do you vote for 2 or 4, or you have something else? You kind of switched. That's what they system that you say, okay, let me do 2.
Yeah.
2. Right, now I'm going to use the red and the blue to draw on that graph. You see, the beautiful thing about mathematical theorems, you can't change them. So, as I am approaching 2, that means I have to go down this line. That means I'm going towards that one. Do we all agree on this? From what we had so far? All right. How about blue? As I approach from the other side, I go to this line right there. I just technically, I'm at 4. You see that the left and right approach are both at 4? What's the limit? 4. Limit is 4. This has nothing to do with anything. This dot. That's a function value. But the limit is there. And these are the best examples for us to learn the difference between pre-calculus answers and calculus answers and what each is good for. Now, to explain this situation, I'm going to talk about collapsed bridge. Right? Yeah, I know, very cheerful example, but education is so good that it produces engineers that make bridges like that. Hashtag Florida. All right, let's go. What do I have? I have a cliff, another cliff over here, right? And there is a bridge. Hopefully this needs to be the same size. There we go. And that's a bridge. The problem with this bridge is that, so I don't know, let's make this a bridge. There we go. Yeah, my design is not the greatest, okay? But we have a bridge. And this is what happened. This portion of the bridge collapsed and it's in the river. Now this is where the river is, obviously. It's all river. And I'm going to take this part of the bridge and put it in the river. You shouldn't be floating in the river, but that's okay. Now, obviously on a bridge like this, you can't charge full toll, right? If the bridge is like 20 bucks, you would charge about 18 because you can't drive the full distance. But now, let's talk calculus versus pre-calculus. This situation is equivalent to a graph that has an arbitrary function with the open circle missing value where the value is dislocated up or down. Doesn't matter. Now, limit is going to help fix this because you can approach from the left, you can approach from the right, arrive at the same location and fix the issue. That's Calculus 1. That's how powerful Calc 1 is. You know what the pre-calc is? Pre-calc only says it's broken. Because that's where the function value is, right? It's in the water. The bridge is broken, the section fell off, it's in the water, right? So the pre-calculus in this concept here only explains that this is broken, right? Where the calculus says, let us approach these values and fix it. Calculus is concerned with all of the values up to the value of interest from both sides. That's what calculus is concerned with. Calculus doesn't care about the point of interest, which was 3 in our previous example, or whatever it is. So, calculus limits allow you to approach the value from two sides of a bridge and fix the issue. Pre-calculus says broken and doesn't do anything about it. So now when I observe this, and let's call this A and this f of x, I have few things to put here. The y value for this A is f of A. So I will say that if I want to compute, which is pre-calc, here's me with the k's, you would have that y equals f of A. Because once you plug in this A into f of x, you get f of A, which is this value here on the y-axis. Now, as I approach from the left, I go on this bump here up, and that goes up to this value here. Romeo, on the other side, goes down this line, and they both arrive at the value L. So, a limit is going to be a limit, well, let's just do limit of f of x as x goes to a is L. In this case, L is not the same as f of a because the value was displaced. So the dot is where pre-calculus value is, the open dot is where calculus value is. Do they compete? No. They just complete each other, right? You can't say this is better than this or this is better than that. Because pre-calculus, in a concept of our bridge, told us it's broken, right? The piece of a bridge fell into the river, and there it is, right? So pre-calculus is going to locate where the broken section is in the water. Calculus fixes the issue, right? Calculus fixes the issue because you can approach from both sides and you can work on fixing so that the bridge is fixed and you can cross it, right? So in our first example, these were equal because the point of interest was there. So our 3, 8 was pre-calculus answer and 8 was limit answer as well. But as soon as you remove the point, calculus answer and pre-calculus answer are no longer the same. Calculus answer is the one where you have these lines going, and a pre-calc answer would be the one that is a solid single dot away from the system. Does this make sense? At least a little bit before you start learning it in depth. So you have a lot of these exercises in the book and in my MATLAB that will address these situations. Here is a raised up sine function or a cosine function. This is a cosine function. Observe this value. It's right there, right? So the limit is 1. The function value is negative 1. Here, limit is 4, function value is 2. And they're not the same. However, on the same graph, if I move here, let's say, the limit and function value are both 5. Because the dot is there. It's not dislocated like here. It's there. So, for this situation, calculus and pre-calc don't match. Function value is here, limit is here. For this point here, or any other point for that matter, function value and limit are at the same location, same y. So pick this point here, limit is 5, function value is 5. Pick this point here, function value 4, limit is 4. That point, both are 2. This point, both are 0. Only for this point, limit is 4, function value is 2. They don't match because it's dislocated. Same for the sine graph or cosine graph here. Only at this point they don't match. At every other point, the function value and the limit value match. So limits compute y values of the function. That's the cheapest we can say. Now, they compute differently. They don't care about a single point. They care about all of the other points around, and then those points will infer what the limit is. So, over here, these points infer to 4, these points infer to 4, limit is 4, even though function value is somewhere else. So don't equate limits to finding just a y value using pre-calc, because they don't always match, as you can see. For most part they do, but not always. We have a left limit, right limit approach. Those are called one-sided limits. And if those are the same, limit exists and it's that value. If they approach different values, limit does not exist. We learned to find the limit graphically. We use our eyes and look at it, the graph, and we learn how to come up with table of values to compute the limit, to either see they both line up with the same number from both sides, or they go with different numbers. The rest is plug and chug, right? You have a lot of these examples with table of values and problems, and you are going to just make sure that they give you the same value or they don't. We are going to finish chapter 2 next class, actually, because the rest of the sections, 3, 4, 5, and 6, some of them are extremely short, to the point, with one application only. So we might be, but we will definitely be done with chapter 2 following Saturday with 2.7 and review and stuff. So this is the time to start thinking about your first exam. I know, I will see you only probably 2 more times before exam 1 is up. So please review pre-calc. Please review chapter 1 in your textbook, especially if you haven't had pre-calculus functions for a long time or ever, but you wouldn't be placing into this class if you've never had them. And stop by office hours if you have any questions. And I will see you all in a week if I don't see you before that. Bye.